All right, today what we're going to do is continue working with systems of equations. Now, what we've done so far is knowing what a system of equations is when you have more than one equation on the same coordinate plane, and we know what the solution of a system of equations is, and that is that ordered pair that makes both equations true, or basically where they cross. Now, what we've done before is solved the system using graphing, and today what we're going to do is use algebra instead of graphing. We're going to solve this system of equations using a method called substitution. So before we jump into solving systems of equations with substitution, we may want to take a little refresher on what substitution is. Okay, so a little refresher course on substitution. Now, substitution is actually the meat of algebra. Okay, so it's when you are replacing one value with an equivalent value. Okay, so the definition of substitution is when we take one value and replace it with another. It's the meat of algebra. So the basics that we used to do is if we had, a equals 5, and we're going to evaluate that if a was -2, right? So if we were to evaluate that if a was -2, and the way substitution works is you take that value of -2, substitute it for a, right, and then we have, well, -2 plus 5. That's the meat, right? That's what substitution is. Okay, and of course you get 3, but that's not the point. Okay, so that's what substitution is. Now, when we're dealing with a system of equations, we will be substituting something a lot funkier. So what if we had something like a plus 5? And what if I was to tell you, well, what if a was actually, z minus 4? What would happen to this whole thing if a was this whole different and crazy looking thing? So the meat of algebra, the substitution piece, where before what we're used to is something simple like swapping out a with -2. Well, here it's something a little bit more complicated. What if a was like this whole other variable and this whole other thing? Well, substitution in principle remains the same. We take our a, but now it's z minus 4. So we make a into z minus 4. So we just substitute with the equivalent value, and we have our plus 5. Right? And then we crunch that, whatever it happens. That's not the point. The point is we can substitute an equivalent value no matter how crazy that equivalent value might be. Okay? So we have this system of equations, and we're going to use that substitution method to find out what's going to happen. So here's how that works with systems. We have two different variables, right? We have two different variables, and we have two different equations. So what we can do is use both of those equations, isolate one of the variables, and then work with only one variable, right? Everything would be so much helpful if we could work with one variable. So can we work with only one variable? Because how are we going to solve a system of equations if we can't even get one variable by itself? So is there a way that we can work with only one variable? Is there a way we can work with only x, or a way that we can work with only y? And when we're solving systems of equations algebraically, that's what we have to think. How can we work with only one variable? So what we can use is substitution. If we can substitute, let's say, y with its equivalent value using another variable, we would work with that one variable. Or if we can substitute x using its equivalent value with y, we can work with one variable. So let me tell you what I'm talking about. So we have these two equations, right? We have x plus 3y equals 5, and -2x minus 4y equals -5. Now, is there a way that we can look at either one of these equations and get one of the variables by themselves? Can we isolate either x or y? Can we isolate x or y? That's the question. Okay. Now, of course we can. We've solved literal equations, right? If we look at this equation here, we could definitely isolate x. We would add 4y and then divide by -2. X would be isolated. We could isolate this y. We could add 2x and divide by -4. It would be isolated. We can even work with this equation. We could isolate this y, subtract x and divide by 3. We can totally isolate x or y. We know how to do these things, but look at this equation. There's a way easier variable to isolate, right? It's so easy to see that we can isolate this x. We can totally isolate that x. It's just one simple step. If we were to isolate that x, it would be so easy. So we see this equation, x plus 3y equals 5. It would be so easy to isolate that x. All we got to do is subtract 3y from both sides. Right? So we have x by itself equals 5 minus 3y. Don't call that 2y if you do smack yourself. 5 minus 3y. 5 minus 3y. Guess what? We have x by itself. Okay, so we have x by itself. That's what we did. We isolated x or y. Now, just like in our previous example, right? If we had a equals z minus, we could substitute some crazy looking thing. We're going to end up substituting a crazy looking thing, right? But here's the deal. We take that variable that we isolated using this equation. Since we used this equation, we're going to substitute this into the other equation. So this is where things get crazy. We're going to take this whole thing and substitute it into the other equation. So we have our x, which is by itself, is actually 5 minus 3y. You know what we can do? We can take that 5 minus 3y value and plug that in for x here. Right? Whoa, this craziness. Just remember, it's the same thing we did with that example. Right? We're going to take one value, switch it out with another value. No big deal. So let's work with that second equation. With the second equation, where we used to have negative 2x minus 4y equals negative 5, remembering now that for this equation, x is actually 5 minus 3y, we can just substitute. So it's no longer x now, right? It's no longer x. It's 5 minus 3y. And we have to use parentheses so that we're sure that we're only substituting the equivalent value and nothing else. We're not changing any other signs. We're not changing any other symbols. We're only substituting the value of x, because x is 5 minus 3y. Well, x is now 5 minus 3y. Okay, so now we've made our substitution. Now we have to evaluate. We have to simplify, then solve for y. Oop. So we simplify, then solve for y. Right? So we have distributive property going on. 2 times negative 5 is negative 10. Negative 2 times minus 3y, positive 6y. And then our minus 4y. And then our minus 5. We can continue simplifying because we have like terms to combine. All right, so we have our minus 10. And then plus 6y minus 4y is plus 2y. And then equals minus 5 there. And then we're solving for y. So we can add 10 on both sides. Plus 10 here. Plus 10 there. So 2y equals positive 5. And then divide by 2. So y equals 5 over 2. You can leave it as 5 over 2. You can call it 2.5 if you want to. It doesn't matter. It just doesn't matter. If you're more comfortable with decimals, use decimals. If you're more comfortable with fractions, use fractions. But there's your y value. So we can pause there for a second and you think, yay, I'm done, right? I'm done. I got my y. Y is by itself. Well, remember the whole deal. We have to remember, what are we doing? We're solving a system of equations. Now, what is a system of equations? It's an ordered pair. You have to remember the system of equations is an ordered pair. Do we have an ordered pair? No. We only have one of the coordinates. We only have the y coordinate now. We need x, okay? We need to find x. So if we only have the y, we need to find x. What do? We can use either of the two original equations. Use either original equation, and then we can find x. Okay, it doesn't matter which one. Okay, you can use the top one, you can use the bottom one, it doesn't matter. So we have our value for y. We can use this equation, plug that y in and find x, or we can use this equation, plug in the y and find x. Now, one of these, of course, makes a heck of a lot more sense than the other. So be smart about it. Wouldn't the first equation make a whole lot of sense? When we have that first equation, x plus 3y equals 5, we take our value for y, plug it in for y. Right? We know what y is. Plug it in, see what we get. I'll use the decimal, why not? So we have x plus 3, but not 3y anymore. 3 times 2.5. And that will give us positive 5. That's what the equation. All we're doing is substituting for that. Right? So all we have to do now is solve for x. Okay, so you got to remember we're looking for an ordered pair. So now we're going to solve for x. Do some number crunching. So we have x plus, and then 3 times 2.5 should give us 7.5. And that will equal 5. And then we solve for x. We can subtract 7.5 on both sides. So x will equal negative 1.5. I think that's what I'm getting. So there's our x coordinate. Okay, there's our x coordinate. So now, what is the solution to a system of equations? Right? Are we done yet? Well, the solution is an ordered pair. So make sure that you're listing your answer as an ordered pair. Remember, ordered pairs look like x comma y. So make sure your ordered pair has the x coordinate first, then the y coordinate. Excuse me. So we have the x coordinate first and the y coordinate. Now, just to be sure, let's check our answers. Remember how to check your answers from the previous lesson. You can plug both in just to make sure we have a true statement. Okay, so I'm going to test it out just in case, because I think I made a mistake somewhere, but I might be wrong. So we plug in our x, and we plug in our y. Does that equal 5? Right? So we have negative 1.5 plus 7.5. Does that equal 5? Absolutely. Check out. This is good. We're good. So everything good. And that's how we find our ordered pair using substitution. And that's substitution in a nutshell. We'll move on to different methods later, but that's it for substitution. Thank you.